So this short video lecture is a continuation in regards to water supply, water availability. The slide in front of you pertains to the consequences of overdrawing groundwater supplies. In the Great Plains region of Texas, Oklahoma, New Mexico, Colorado, Kansas, Wyoming, and Nebraska, the groundwater system supplies irrigation water to over 10 million acres. In this region, the groundwater withdrawal rate is 100 times greater than the recharge rate to the groundwater system. Hence, the water table for the groundwater system has dropped over 200 feet and continues to drop at a rate of about 6 feet per year. The deeper groundwater table makes it more expensive to drill deeper, higher cost irrigation wells. Over the next 20 years, another 3 million acres of farmland will be abandoned or converted to dryland farming due to inadequate availability of water resources in the region. So lowered groundwater table is one consequence of overdrawing the groundwater resources. The second bulleted item pertains to land subsidence. Subsidence occurs when the groundwater that filled the openings in the soil and rock is removed, and hence those openings collapse. The end result is the land surface sinks or settles to a lower elevation. In the San Joaquin Valley of California, the land has settled as much as 28 feet, which has then damaged pipelines, railroads, highways, homes, factories, and water distribution canals or aqueducts. The photo on the right illustrates the amount of land subsidence in the San Joaquin Valley of California. A USGS scientist stands at the base of a pole, and it's showing you the land subsidence from 1925 until 1977 due to overdraw of the groundwater resources. The land subsidence has ranged between a foot to 28 feet in some areas. This is indicating about a 28-foot drop in land subsidence because of overdrawing groundwater. This is just another picture of another USGS representative depicting that between 1988 and 2013, land subsidence at this location has been almost 5 feet or 4.8 feet. So we have various aquifers throughout the United States, which was depicted in an earlier slide in a previous short video lecture series. This diagram is depicting areas of groundwater overdrafts in the United States. Red means there's a high groundwater overdraft. Yellow means that there's a moderate groundwater overdraft. So what's being shown in this blow-up portion of the figure is water level changes in meters. So the reds indicate more than 45 meters in water level change, and then it decreases with the various shades of yellows. The red zone indicated here with high overdraft and the correlating blow-up version of that depicts the Ogallala Aquifer. This is considered to be a sole source aquifer in the region of Kansas, Colorado, Oklahoma, Texas, and New Mexico. In parts of the Ogallala Aquifer, groundwater is being pumped out at 10 to 40 times faster than the natural recharge rate for the groundwater system. Hence, we're seeing lowered water tables as much as 45 meters. Pumping from the aquifer has increased rapidly after our industrialization and World War II because we now have efficient deep well pumps, and it's low cost energy to run gasoline or natural gas engines. We also have inexpensive aluminum piping and central pivot sprinklers and other water technologies that allow increased irrigation of farms, which requires more water to be pulled out of the groundwater system. So basically, there are 170,000 pumping wells in this Ogallala Aquifer area that remove about 19 million acre feet per year to irrigate over 65,000 square kilometers of farmland. So again, one of the side effects of this is water table declining in the subsurface. Irrigation acreage is declining because there's a challenge to provide the water for the farms, and the cost of pumping has increased. Now we're going to focus specifically on California and the drought that recently occurred in California. Throughout history, California has experienced many droughts. There were droughts in 1841, in 1864. Between 1928 and 1935, there was a 7-year drought. Between 1947 and 1950, there was a 3-year drought. Between 1976 and 1977, there was a 1-year drought. But most recently, California experienced a drought between 2006 and 2010, which was 4 years. Then they got a reprieve for 2011 because they had good rainfall and snowfall. But that 1-year break didn't allow them to recover fully, and now between 2012 and 2017 has been the most recent drought. So excluding the year 2011, California has been in a drought scenario since 2006. California is also the most populated state in the United States and a major agricultural producer. So the drought in California can have a severe economic as well as environmental impact. As far as the worst years for the drought, they occurred in 2014 and 2015. Over 95% of California's 43 billion agricultural sector was experiencing severe, extreme, or exceptional drought, with the livestock sector more directly exposed to exceptional drought than the crop sector. So the agricultural industry was definitely being impacted by this. So the water in California is very closely managed. It's got an extensive pipeline network to serve the most populated areas of the state as well as the most dry areas of the state. Rainfall is limited in California, and it can vary of about 40 inches per year, depending upon what's going on with the meteorological conditions in the area. So the graph in front of you shows the cumulative changes in groundwater storage in millions of acre feet on the y-axis. And obviously here's 0, so if it's down in this region, it's a negative change in storage, meaning they're losing storage of groundwater. And then this is the water year or timeline, basically. And when looking at this diagram, it appears that the cumulative groundwater storage has decreased over time, and we're still considered to be in a negative scenario regarding groundwater storage. Now, the green depicts surface water deliveries in millions of acre feet, meaning the amount of surface water that was delivered to various areas throughout California. And you can tell that that has continued to increase gradually over time, except that we've had some really dry years here. Here's a period of drought, here's a period of drought, and then this is depicting our most recent current version or period of drought. So the surface water supplies have tended to increase, and that's because of increased demand for water. By the way, the picture up in the top right corner is a picture of a lake, non-drought condition, and then this is under drought condition. So I'd like to again remind you that California has experienced the worst drought in over a century between 2011 and 2017. And the period between 2011 and 2014 was actually the driest in California history since record keeping began. So the hydrology of present-day Central Valley in California is driven by surface water deliveries and associated groundwater pumpage, as mentioned earlier. These can actually impact spatial and temporal variability in climate, as well as water availability and land use. Since the early 1990s, the availability of surface water has decreased because of operational changes of the Federal Central Valley Project and the California State Water Project. Although irrigation has become more efficient, since 2000, land use in the Central Valley has trended toward the planting of permanent crops like vineyards and orchards and replacing non-permanent land uses. During the recent droughts in 2007 through 2010 and 2012 to present, groundwater pumping has definitely increased from the combined effects of these changes. Again, as mentioned previously, the increased piping has caused land subsidence to occur. The graphic depicts some telltale signs of drought where the blue dots indicate water level decline in wells. So some of these larger dots, the wells have experienced greater than a 200 to 400 feet decline in water table. There's been a few which have actually experienced an increase in water table that are scattered throughout the area. The yellow dots depict areas where the land has actually uplifted, maybe an inch, but the orange dots depict areas of land subsidence greater than 5 inches. So we've got land subsidence occurring in some of these regions. So after more than 5 years of drought in California, the year 2017 has seen above average rainfall and snowpack, which inspires many to ask, is the drought finally over? Well, in April of 2017, Governor Jerry Brown issued an executive order officially ending the drought state of emergency in all of California counties except for a few: Fresno, Kings, Tulare, and Tulameen. Hydraulically, however, the answer to this question requires consideration of California's 3 primary sources of water: surface water, snowpack, and groundwater. So let's start with surface water. Rainfall in 2017 has filled the majority of California's major reservoirs to above historic levels. Likewise, as the USGS stream gauge network shows, flows of a majority of the streams have been at or above average for the last 4 months. This indicates that most of California's rivers, creeks, lakes, and reservoirs are considered in good condition. Now let's look at snowpack. On average, the Sierra Nevada snowpack supplies about 30% of California's water needs as it melts in the spring and summer. A series of back-to-back storms blanketed the Sierra Nevada in January and February of 2014. As of May 2017, statewide snow accumulation data indicates that the snowpack in northern, central, and southern Sierra is 190% of the normal for this date, so it's definitely good news. As far as groundwater is concerned, the groundwater aquifers recover much more slowly than the surface water. Among other things, how much and how fast the water can recharge. Unlike surface water, which can recover just during a few days after a heavy rainfall event, groundwater aquifer recovery takes years or decades. So, in terms of California, the groundwater levels have not recovered yet, and it's uncertain as to when they will recover. This diagram depicts the exceptional drought condition in 2016, and then after January storms occurred, about 49% of the state was considered to be out of the drought situation because so much rainfall occurred. So after more than 5 years of drought in California, 2017 has been above average rainfall and snowpack, and the state has officially ended the drought state of emergency during the spring. Rainfall in early 2017 has filled most of California's major reservoirs to above historic levels, and the U.S. stream gauge network shows that flows in a majority of the streams have been at or above average for most of the last 4 months in early spring. So the surface water part's fine. Also, in snowpack, the Sierra Nevada snowpack, which supplies about 30% of California's water needs as it melts, was above average. And the statewide snow accumulation data indicated that the snowpack in northern, central, and southern Sierra was far above normal for this date. So hence they took the state of emergency off in regards to the drought. Now, one side effect of this was the Oroville Dam in California, which is known as the tallest dam in the United States, became filled to capacity, and they had to release water through an emergency spillway. Well, because of the amount of water that they had to release, there was a failure in the spillway and a large gap occurred, and they ended up having more water flowing around the spillway and causing turbidity problems for downstream. This was in the news, and there was concern that the entire dam might fail, but fortunately they were able to get the water levels down behind the reservoir dam and hence stop using this emergency spillway, and now they're working on repairing and fixing it. But that is a side effect of the drought that happened in California with the heavy rains that happened in the spring.